in the last class we were dealing with the flow K theory, by which one tries to assess the stability of periodic orbits. So, if you have a periodic orbit like this, the way to understand the stability is start from some initial condition. That means, this is x at t naught, and then as you go around this orbit, you end up here at x at capital T. Then the whole period is t minus t naught. The way to understand the stability is to express x at capital T as some function phi times x at t naught, and this phi will be dependent on the initial time, the initial value and the total time. So, t x naught t. This particular thing is nothing but a matrix, because here you have a vector that times a matrix gives the final vector. This matrix, as we told, is the monodromy matrix. And the eigenvalues of the monodromy matrix are the flow K multipliers. So, ultimately the job is to identify this matrix and obtain its eigenvalues. Now, as we have said that if you are evolving something from here to this point, say I have x a and here I have x b, then x b when expressed in terms of x a is x a pre-multiplied by the state transition matrix. Okay. So, that is how we understand in standard control theory. So, x b is the phi, the state transition matrix times the state x a. So, that is the concept of the state transition matrix. Then we will write x b is equal to phi a b times x a. Okay. Now, if we write this, then it is also true that if you take a perturbation from here and that ends up as a different perturbation, say here, then this perturbation, the delta x b can also be expressed as phi a b delta x a. So, the way states are related, the perturbations are also related. Okay. So, we will essentially follow this up in order to develop the concept of the monodromy matrix. Now, in the last class we had started saying that here if you have a state x a, then suppose it goes to state x b and then it continues to state x c, or in other words it goes from x a to x c, in between a state is x b. Then you can write as we have just done, x b is equal to phi a b x a. You can also write x c is equal to phi b c x b. So, these are the individual state transition matrices. Then you can write x c is equal to phi a c x a from here to here, and then your phi a c will be nothing but phi b c times phi. So, simple affair then. You have the flight from x a to x b to x c. Then if you want to obtain the state transition matrix from A to C, it is just a multiplication of the state transition matrix from A to B and B to C. So far so good. This is the general theory that you learn in standard control theory texts. Now, these state transition matrices, what are these? If in case this the system is linear time invariant LTI, then your phi going from t, starting from t naught will be, starting from t naught, flight over a time of t will be, or t naught to t will be exponential matrix A t minus t naught. So, here this A is a matrix. So, this is a matrix exponential. The way matrix exponentials are treated, I do not have the time to discuss it in details here, but this can be found in any standard control theory textbook. Essentially, the way we handle the exponential, any exponential, we handle the matrix exponential in the same way as a expansion, binomial expansion. So, this can, if you know the matrix A, that means, if you know the elements of the matrix A, and if you know the starting time, the ending time, then you can evaluate this just as a number. And in MATLAB, this matrix exponential evaluation is given by the XPM function. So, all you have to give is EXPM within bracket, and you have to give whatever is in the exponent. So, this is the simple thing, and if you know this, then you can easily write delta x of t, that means, the perturbation at time t is e to the power a t minus t naught delta x at t naught. Okay. This is nice, and this tells you that if you have a orbit something like this, then if you can start from here, go up to here, and if you can calculate the state transition matrix from here to here, and then if you can come back, then all you need to do is to multiply this state transition matrix and the state transition matrix to obtain the total state transition matrix of the whole cycle, or you can break it up into further segments, say 5 segments. In that case, you have to go from here to here, obtain the state transition matrix, go from here to here, obtain the state transition matrix, and then multiply all them. No, it does not work. It does not work if you have a non-smoothness in this orbit. Let us come to why. Suppose you have an orbit going something like this. Say here is a switching manifold. It starts from here and it hits like this, and then it goes like this, and this is different. The vector field is different, and then it goes like this. So, this is the starting point, and here you have the vector fields different in the sense that if you draw these two tangents, they will be different. If you draw these two tangents, they will be different. In that sense, the vector field just before crossing and the vector field just after crossing are different, and that is exactly what happens in most non-smooth dynamical systems that we have already seen. The question is now, if you say that from here to here my state transition matrix is A1, from here to here the state transition matrix is A2, from here to here the state transition matrix is A3, then you cannot say that means you will write delta x of, say here it was hitting at tau 1, here is tau 2, starting at 0, ending at t. Then x tau 1 is a 1 delta x 0, delta x tau 2 is a 2 delta x tau 1, and delta x t is equal to a 3 of x tau 2. If this is how the a 1, a 2 and a 3 are defined, then you cannot say that the product a 1, a 2, a 3 this is actually not equal to. This is important, because most people make a mistake at this point, that these are not the same. Why? The reason is something like this. When you are starting from here, when you are writing this, delta x naught, you are essentially saying that I am considering a perturbation, and then when you are reaching here, you are saying that this is how my perturbation is flying. And then at this point, the original trajectory reaches the switching manifold, and the perturbation is something like this. But then after it starts, you see that all the points on the perturbation do not reach the switching manifold at the same time, they reach at different times, and therefore, after the perturbation when you start from a different ellipse, and then you go on coming to this and you get an ellipse. Here also you have some kind of a different ellipse to start with, and then that goes on. And when it reaches here, whatever is the size or the shape of the ellipse, that is given by the total monodromy matrix. That means, the initial ball times the initial ball means you consider a circle or a sphere, and then pre-multiply that by the monodromy matrix gives you the final ellipse or ellipsoid, and that tells you whether or not in any particular direction it elongates or shrinks, contracts. If it contracts in all the directions, then it is stable. If it does not contract in all the directions, that is unstable, and so on and so forth. But it is not difficult to see that since all the points, all the perturbed trajectories do not reach the switching manifolds at the same time, therefore, this will not be valid. This will not give the monodromy matrix. That was valid for this case, because there was nothing like a switching. So, if you consider a perturbation that evolving here, and then that continuing to evolve here, essentially it is the same continuous evolution, and that is exactly why it worked, but in this case it will not work. In that case, how to handle it? When we try to handle it in that situation, essentially let us start in a neighborhood of the switching manifold. Say here is a switching manifold, and here is a part of the orbit that reaches the switching manifold. It starts from a point, say x naught, and reaches at I will write it here, x t. Tp is the time when it reaches, 0 is the time when it starts, and Tp is the time when it reaches, and then it goes off. Okay. There is a part of trajectory that starts from this point, and it also goes and reaches, and this from this point it goes off. So, the blue one is the original trajectory, and the green one is the perturbed trajectory, and the perturbation is given by this vector, and this vector is delta x naught. So, the perturbed trajectory is x naught bar, and this is delta x naught. When this fellow has reached the switching manifold, this fellow has not reached, and supposing at that time when it is here, this fellow is here, say. So, you can draw the perturbation like this at this point. Okay. So, what is this particular value? It is x bar, which is at the time t p, right, and then after some time it reaches the switching manifold and then it goes off. Okay. When it reaches the switching manifold, this fellow has already crossed and has come to some distance, say here. So, at that point you can draw the perturbation. Now, this perturbation here is delta x, we will call it p minus, and this perturbation we will call delta x p plus. Essentially, we are interested in how the perturbation evolves across the switching manifold, and you can see that this perturbation is wholly in this side of the switching manifold, and this perturbation is wholly in that side of the switching manifold. So, we are trying to find out how this one maps to this one, or in other words, we are trying to find a expression so that we can write delta x p plus is equal to something times delta x p minus. That is how we are trying to express. So, what we are trying to express? We are saying delta x p plus is something times delta x p minus. Once we do that, then this is the state transition matrix across the switching surface, this term. We will do that. Fine. Now, a few things we need to write. What is this? This is this particular point is in green, x bar, this is at T p bar. T p bar is the point at which it reached the switching manifold. So, this one is x at T p bar, x at T p bar. Fine. So, this is the setting in which we are trying to do things. So, let us carry on. First thing, what is x naught bar? That means perturbed trajectory. X naught bar is x naught plus delta x naught, right? Clear? Now, we need to find out this perturbation and this perturbation. So, what is this perturbation? Delta x p minus is this minus this, x bar t p minus x t p, right, and this one delta x p plus is equal to this one x bar t p bar. T p bar is the time at which this trajectory reaches the switching manifold minus x T p bar. Okay. So, these are the three equations that we can easily write, basically relating these two. So, since we are interested in this equation, we are interested in the right hand side, how it will ultimately come up. Now, you see x T p bar, this one, x T p bar is this one. So, x T p plus it has evolved through this. So, if your vector field in the left hand side is f p minus and the right hand side is f p plus, then it has evolved through the right hand side vector field. So, this is x T p plus, in the first order approximation, you will have f p plus times the time that is taken, that is delta t. So, this plus the vector field times the time that is taken. Similarly, this point here x bar T p bar is this x bar T p plus f p minus and the flight time. Okay. X bar T p, x bar T p is here. So, we can substitute. So, we can write this is equal to x T p plus delta x p minus plus f p minus delta t. So, we have expressed these two. Good. Next step. Keep this thing in mind, so that we can will need to refer back to it. Now, we start from delta x p plus. This is what we are trying to find out. We are trying to find out this. This we have already seen that this is x bar T p bar minus x T p bar, and the two right hand sides that also we know. So, we will express it as x bar T p bar is here and x T p bar is here. So, we will substitute these two, and thus we get x T p plus delta x p minus plus f p minus delta t minus x T p minus f p plus delta t. These two cancel off, and so we are left with delta x p minus plus f p minus delta t minus f p plus delta t. Essentially, this minus this times delta t. Okay. So far, so good. Now, you notice that if we drop a orthogonal here, then you notice that delta x p minus times the normal to this switching surface is equal to, this is f p minus delta t, normal times the f p minus delta t. So, if you take its component here and its component here, they are just opposite to each other, and the components are obtained by taking the normal to the switching surface. So, the normal to the switching surface is n, say n is here. So, n times this vector is equal to negative of n times this vector, right. So, we can logically write n transpose, because n will be a vector, it has to be transposed in order to multiply with it. This times f p minus delta t is equal to minus n t n transpose delta x p minus, okay, delta x p minus. This can also be, if you are not convinced, this can also be obtained from the condition that this evolution satisfies the condition for the switching manifold at this point, and this evolution satisfies the condition of the switching manifold at this point, and switching manifold is beta x equal to 0. So, we can write beta of x T p equal to 0 as the condition when this is satisfied, and beta x bar T p bar equal to 0 as the condition when this is satisfied. Now, you can take this and expand this. So, you can write, I will write 0 in the left hand side, 0 equal to beta x bar T p bar, will expand it, beta x T p plus beta x bar T p bar is just from here, we already have it, plus delta x p minus plus f p minus delta t, and this can be taken out, and this can be written as beta x T p plus n transpose delta x p minus plus f p minus delta t. Okay. Now, this term is 0 because of this. So, you get this, which is the same as writing this. So, at the end of the day, what have you? You have delta t expressed as minus n transpose delta x p minus divided by n transpose f p minus. Okay. So, this is the expression for the time taken, additional time taken by the perturbation to reach the switching manifold. Now, once we have it, things fall in place, because we started with this, we wanted to express this, and this was ultimately expressed as here. Okay. So, we will start from here, we will write, just keep this in mind. Okay, I will write here, delta x p plus is equal to delta x p minus plus okay, f p plus minus f p minus times, see, times minus delta t. Can you see? If you take delta t out, it is f p minus f p plus. We are putting the negative sign out, so that this get cancelled off. So, this times n t delta x p minus divided by n t f p minus. Okay. Now, what are we driving at? Ultimately, we are driving at this, and you can see that we have it really. We are trying to find this, which is delta x p plus divided by delta x p minus. So, if I divide now both sides by delta x p minus, we have it. So, we will write your this particular thing, which is called the saltation matrix. We are actually trying to express it as delta x p plus is equal to saltation matrix S, times delta x p minus. So, what is the definition of the saltation matrix? It is the state transition matrix across the switching manifold, that is called the saltation matrix. Saltation, the word means jump. So, it is just nothing but a jump matrix. In some literature you will find the word jump matrix. So, you can easily see from here, then the S will be this will be divided by x p minus. So, it is I plus x p minus has been divided by. So, this goes off, you will say it is f p plus minus f p minus bracket times n transpose divided by n transpose f p minus. So, this is the saltation matrix, this is the expression for the saltation matrix. Now, in deriving this, so this is important, keep this in mind. In deriving this, we had assumed that this surface is static. We did not assume any movement of the surface, but in general it can move. For example, the switching manifold, the switching surface, there is no reason to assume that it will be always absolutely static. It is possible for it to move. In case of the impact oscillator, the impacting surface can move. In case of the switching circuits, the condition for switching can be a moving surface. So, that is all actually not only possible reality. In that case, the expression will turn out to be, in general, will turn out to be I plus the numerator remains the same, f p plus minus f p minus n transpose. Here it will be same thing, n transpose f p minus, but additionally there will be one term that relates the rate of change of the switching surface. So, will be the partial derivative of the switching surface with respect to time calculated at t is equal to T p. So, this is the total final expression for the saltation matrix. Once we have it, things will become rather simple, because let us come back to the condition that we took. Leave it, let me draw it again. Here is your switching surface and here is your starting point. You go up to this point, come up to this point, and say you go up to this point. So, this is the evolution. In that case, this is the starting point 0, this is the ending point t. So, suppose your evolution from here to here is given by a1, from here to here is given by a2, and from here to here is given by a3. So, the state transition matrix from here to here up to the time t tau 1 up to the time tau 2, 0 to tau 1 is a1, tau 1 to tau 2 is a2, and tau 2 to capital T is a3. In that case, as I told you, you cannot say that the total monodromy matrix is a1 times a2 times a3. Here at this point, there will be a saltation matrix, say let us call it S1. Then there would be another saltation matrix at this point, S2. Then the monodromy matrix M will start from the this one in the right hand side, A1 times S1 times A2 times S2 times A3. Okay. Notice the order in which we are writing. It is starting from the right, proceeding to the left as you go around the whole orbit. And it is very simple to do the same thing for an orbit something like this. If it is a complicated orbit, higher periodicity with a number of switchings, it is nothing but you start from a point and you find out this state transition matrix from here to here, and then at this point you again obtain the saltation matrix, again the next flight, again the saltation matrix, again the next flight, and then you simply multiply them. That is how you obtain the monodromy matrix, and the eigenvalues of the monodromy matrix will be the Floquet multipliers. That is all. And if the Floquet multipliers are inside the unit circle, you have a stable periodic orbit. If they are outside the unit circle, you have a unstable periodic orbit. Okay. So, this is how we actually find out the stability of periodic orbits, and in case of the non-smooth dynamical system where there is some kind of a switching, this is the complication ultimately that can easily be solved, and ultimately you can obtain the monodromy matrix. Now, as I told you, we were considering border collision bifurcations, in which the ultimate thing that we need to evaluate is how do the eigenvalues change as the fixed point goes across the unit circle. There, an orbit like this will be just a fixed point of the corresponding Poincare map, and the eigenvalues of the fixed point will be same as the eigenvalues of this. So, when such a orbit crosses the switching boundary, that means if you imagine that there was an orbit something like this, and as you change a parameter it crosses and it becomes something like this, then there has been a change. There was only one excursion to this side earlier, now there are two excursions here. So, in between there has been a border collision event, a grazing event, which is nothing but a border collision event, and naturally in order to understand that border collision event, you will have to find out the eigenvalues of the fixed point in the discrete map. So, the discrete map is obtained something like this. You have got a Poincare section and you locate the position here, and here you locate the position here, and you are interested in the Floquet multipliers, you are interested in the eigenvalues of that fixed point, which is nothing but what we just obtained. So, in one case you will have to obtain the eigenvalues of this orbit, its Floquet multipliers, and here in this orbit, and that these two Jacobian matrices will need to be substituted in the theory that we already presented, and there the theory will predict what will be the outcome of this bifurcation. This is how we apply the theory to a particular concrete situation of a non-smooth dynamical system. Is that clear? Okay, fine. So, we have learned how to handle non-smooth dynamical systems, and okay, then let us now go to another topic, because we have more or less in details covered the issue of this. Let us now treat the problem of how to actually do experiments in nonlinear dynamics. Experiment means where you are trying to construct something, you are trying to observe its trajectory in the state space, you are trying to observe how it looks on the Poincare section, you are trying to observe how it looks when you draw the bifurcation diagram. That means some way of experimentally obtaining the bifurcation diagram. In many cases, we have already treated that. In many cases, you will need to reconstruct the dynamics by state space reconstruction technique, but that apart, how to actually do the experiments. Now, let us consider this one by one. First, let us assume some kind of a generic experiment running inside this box. What does it mean? It means that supposing inside you have got a Chua circuit, there is some kind of a oscillation going on in the voltage and the currents. If it is some kind of a electrochemical oscillation, so there is a container in which the constituent components, constituent reagents are changing in their concentration as a dynamical system. If you have a mechanical dynamical system, you have got some physical mechanical component moving, and ultimately you have got these, and you get some kind of a sense of that. What I mean by sense of that means, if it is a electrical system, you have some way of measuring the voltages and the currents, and the currents are also very often measured as voltages by passing it through a standard resistor, so that you get a voltage proportional to a current. If you have some kind of mechanical system represented by, say, the position, the momentum, the pressure and stuff like that, all these need to be ultimately converted to some kind of a voltage signal. So, you need transducers. If you have a electrochemical experiment going on, that also needs to be converted to some kind of a electrical signal in order to actually observe it. Now, let us first illustrate it with reference to a electrical experiment, some kind of electronic circuit in which you are observing these. So, what are the results of the observation? Results of the observation is some voltage at some points, some voltage at another point, and one of these voltages may be a current proportional to a voltage. And then we can put that on to the CRO, right? And in the CRO, you will find that there are a few ports where you can put. There is the X port and the Y port. So, if you put it in the X port and measure it against time, you will see some kind of a oscillation like this. So, here is your time, here is your X. There is a knob that you can turn in order to plot it in the X Y mode. If you do that, then you get, and you have to put the other variable also in the Y mode, Y channel, then you get what is actually the orbit in the state space, not exactly that. Suppose this is a higher dimensional system, but you are observing only 2, then it is projection of that in the direction of this x y. So, you might imagine that it is actually 3-dimensional system with some kind of a oscillation going on, but when you take your say x coordinate and the y coordinate, then you are essentially looking from here as if your eye is here, and you are seeing the projection of it in the x y plane. That is what will be observed here. You will not be able to actually observe the 3-dimensional thing, because for that requires a different visualization technique. It is possible to do a data acquisition and plot this on a computer in 3D, that is possible though. So, you have a plot of the phase plane. If you see it something like this, you know that it is a periodic orbit. If you see something like this, you know it is period 2 orbit. If you see something like this, you know it is period 3 orbit, and so on and so forth. But supposing the system is okay, suppose you want to observe it on the Poincare section, what do you do? As you know, the Poincare section can be obtained in 2 possible ways. If it is a autonomous system, you will have to place the Poincare section physically. That means, if it is an autonomous system and you have some kind of orbit like this, and you have to choose a particular value at which you place the Poincare section, say here. What does it mean? This value corresponds to some particular value of a coordinate, say z. So, a particular coordinate satisfying a specific value is equivalent to placing the Poincare section. So, what will you do? You will sense these, and and these will have to be compared, that means the z coordinate value, z coordinate signal has to be compared with a given DC voltage corresponding to this level. You get the point? The point is that here you have the x coordinate, here you have the y coordinate, here you have also the z coordinate, and you are placing the Poincare section such that whenever z is say 1, then I observe it. What does it mean? I will have to take the voltage corresponding to the z coordinate, say this is the voltage corresponding to the z coordinate, I will have to compare with a signal 1 and I have to put a comparator. So, whenever this comparator changes sign, you know that it has been crossed, okay. But you are not trying to observe it in both the directions, you are trying to observe it when it crosses from one side, which means at this point you will have a signal something like this, out of which you either choose the positive edge or the negative edge, but not both. Okay. So, you either choose the positive edge or the negative edge, but not both. So, whenever this is happening, you need to observe the x and the y coordinates. So, you are actually not trying to observe the z coordinate ultimately, you are trying to observe the x and the y coordinate when a specific condition on the z coordinate is satisfied. So, what you do, essentially you will have to, suppose you are trying to observe it at the positive edge, then you need a ultimately from here you need something like this. At this point you want to observe, at this point you want to observe, at this point you want to observe. So, you need a very sharp impulse at these points. You need very sharp impulses at this point, okay. Meaning that I want it to be observed at that instant. How do you obtain sharp impulses from this? It is rather simple. All you need to do is to put a differentiator. If you put a differentiator, at this point it will give a spike, at this point it will give a negative spike, at this point it will give a positive spike, at this point it will give a negative spike and all that. Put a diode, eliminate the negative spikes, you get only the positive spikes at the point where you want to observe it, right. So, you have a sequence of spikes, you have a sequence of impulses at the points where you want to observe it. Now, in a normal CRO you will find that at the back of the CRO there is something called a Z modulation port, where if you put this signal, then it will make the CRO observe the x and y coordinates only at those instants when it is positive. Okay. So, the simple way of doing it is that in the CRO, here is the screen and here is the x and the y, put x and the y, but also at the back put this signal at this Z mod port. In some CROs you will find that it observes when it is 0, some CROs observe when it is positive. So, depending on the specific CRO that you are using, you might need to put an inverter. That means, you will need to make this value 0 when you want to observe it, else it is a positive value. That depends on the model of the cathode ray oscilloscope that you are taking. So, here is the x port, here is the y port, you take the x port and y port, put these things. So, what you do? Ultimately what you get on the screen, you see dots. Where are the dots? That is when x and y are observed at these instants, which means you have done the sampling, you are observing it on the Poincare section. So, whatever appears on the CRO screen is the phase portrait in the discrete time. Okay. So, this is actually how the observations are done. In mechanical or other domains, essentially the same procedure has to be followed, only you need to get x, y, z as a voltage signal. Okay. Now come to the point how to obtain a bifurcation diagram on a CRO screen. For obtaining the bifurcation diagram, say something like this. What is your x axis? Is a parameter, and what is your x axis? Is a variable. So, this variable could be x, y or z, and these are, as I told you, have to be obtained as a voltage signal, but parameter then also has to be obtained as a voltage signal, then only you can put it on the CRO. Now, some parameters are naturally a signal parameter. For example, if there is a reference signal that you are giving and that itself is being used as a parameter, you can use that, or a circuit in which you are applying a input voltage which is variable, that is a parameter. So, that can simply be taken as a x axis coordinate. Why? Because then that is already available as a voltage signal. In the cases where you do not have a parameter directly available as a voltage signal, you have to cook up some way in which it is converted into a equivalent or proportional voltage signal. Suppose a resistance is varying, then how to do that? You will have to use a two limb rheostat. One limb is your load, the other limb varies at the same time, and you apply a voltage, you allow a current to flow, and depending on the resistance you get sense the voltage. So, there are various ways of actually doing it, but the essential message is that ultimately you have to obtain the parameter also as a signal. Now, put the parameter, the voltage corresponding to the parameter in the x coordinate of the CRO. So, here is the screen, here is the x and the y. X will now be the parameter, and put the y coordinate as one of the variables. For example, x, y or z, you take one of these and put in the y coordinate. Normally what you will see, for a specific value of the parameter you will get just a point if the orbit is period 1, because parameter has a specific value, and if it is a period 1, then the sampled value also has a specific value, sampled. That means, here you have already put this particular signal in the Z modulation port. That means, you are not observing it continuously, you are observing it in the Z mod. Okay. Then, as you change the parameter, that means, you change the input voltage, change whatever is the parameter, then this coordinate will change. As a result, this point will move, and as well, suppose this orbit goes through a period doubling, then what will you see? As the parameter reaches a particular value, you will see there are two sampled values for the state y, again 2. So, you will get something like this. Again, if it goes into period 4, it will get something like this. If it is chaotic orbit, you will get a smudge. So, the whole bifurcation diagram actually appears on the CRO screen, but not at the same time. As you move, it actually sweeps through. This bifurcation diagram actually sweeps through, right? And when it comes here, this is no longer there, it has vanished. So, how to capture the whole bifurcation diagram? In the olden days, we used to take a camera, switch everything off, all the lights off, take the camera and make a very long exposure. That means, it's kept open so long as it is being given a sweep. So, this parameter is given a sweep, and it ultimately captures the whole bifurcation diagram on the film. Develop it and you have it. Nowadays, you have got the digital storage oscilloscopes, where you can store. As you give the sweep, you can store. So, ultimately you see the whole bifurcation diagram on the computer screen. Okay. This is another nice way of doing it, but one word of caution, the digital storage oscilloscopes measure the actual signal and the noise with equal intensity. So, if the system is noisy, then you will see a lot of smudge around this if it is done with a digital storage oscilloscope, while in analog oscilloscope the actual signal is brighter than the noise signal. So, you see the bifurcation diagram better with the analog oscilloscope, but nobody nowadays does it because of because it is somewhat cumbersome to switch lights off and put a camera and do this slowly. The other way of doing it is that if you have a parameter, one way of giving a sweep is to generate a signal that is stepped like this. That means, this parameter, instead of actually slowly varying it, you give a stepped input. How do you do that? You can generate a stepped signal and use that as a parameter. And if you do so, then what happens is that exactly the same thing that you do in a simulation. What you do? You change the parameter and then you observe it, again you change the parameter in another step, you observe it. So, that is how we do. If you give this kind of stepped signal as the parameter, it automatically observe it, and say after some time it falls and then it goes like this again. Again falls. What will you see on the screen? It will be swept. The sweep will go on, and you will see the image static on the screen, image of the bifurcation diagram static on the screen. That is another nice way of doing it. Okay, I will call it a day today, and we will continue in the next class.